whenever doing any modelling, we just get the information that we've got, we put it down, highlight the key information, and then see where we get to. So we've got a rectangular vegetable garden. So what do we know about rectangles? We've got 20 metres of fencing of wire, and she's going to cover 3 sides of that fence. Existing timber forming the fourth. Calculate the maximum area. So what have we got? We've got a rectangle. We have to work out an area, and we've got fencing wire to go around the outside. So if we have a quick sketch of what we've got, if you like, that's our fence, and there's our wire. So typically there's the wire going around the fence, and we know the area of a rectangle is length times width. So we can't do much when we have x and y, so we need to use this information here to find some form of relationship between the length and the width. And the key is this 20 metres of fencing. So these values here, the 2x plus y, has to be used with the 20 metres of fencing. So if we just rearrange that, we can see y is equal to 20 minus 2x. So now I can use that information and substitute that into the rule for the area. It's equal to x times the y value, and the y value is 20 minus 2x. So now I've got a rule for the area. Let's take a 2 out the front, is 2x times 10 minus x. So if I sketch that, so I've got a negative sign there, I've got an intercept at 0, I've got an intercept at 10, and this is the area, and that's the side length x, which means I'm only interested in sketching the graph over this section here, because this represents a positive area and positive values for the x. So if that's 10, my maximum is my turning point, and I know my turning point occurs at 5. Okay, halfway between 0 and 10. So therefore the maximum is at x equal to 5, and if x is equal to 5, substitute that into there, y will equal 20 minus 2 times 5, which is equal to 10. And in fact, the dimensions of my rectangle are 5 by 10, using the rule for my area. The area is length times width, which is 5 times 10, which is 50 metres squared of area. Okay, let's have a look at 24. We've got a cricket ball is thrown by a fielder. It leaves the hand at a height of 2 metres above the ground, and the wicket keeper takes the ball 60 metres away at a height of 2 metres above the ground. It is known that after the ball has gone 25 metres, it is 15 metres above the ground. The path of the cricket ball is a parabola. Find the rule for that. Okay, so let's have a quick sketch. In fact, we might change that. So we start 2 metres above the ground. We throw the ball to someone 60 metres away. That's also 2 metres above the ground. And then after it's gone 25 metres, it's 15 metres above the ground. So in terms of coordinates, that's the point x equal to 0, 2. That's 60 metres later. So you can see there that we've got three equations, three bits of information to satisfy our ax squared plus bx plus c. Again, typically a CAS, but because we've got a nice intercept here, we can probably solve it not too badly tech-free. So if I use this for equation 1, x equal to 0, y is equal to 2. So if I put that in, 2 is equal to a times 0 squared plus b times 0 plus c. So clearly c is equal to 2. So that makes working these other ones out a little bit easier. Equation 2, I've got 1525. So 15 is equal to a times x squared plus b times x plus 2, because c is 2. And equation 3 gives me 2 is equal to a times 60 squared plus b times 60 plus 2. So we can see here from these two equations here, we can solve them simultaneously. I think we'll put those equations in the CAS. I'll do that, and I'll paste an image of what it is we should have got. As you can see, I've added the CAS calculator output from putting in our system of equations. Type them in carefully, check them, and you can see there that our A value, B value and C values are there. Now, since we've got access to our technology, the next best thing really is to define a function in our CAS and sketch the graph on our calculator so we've got a good idea. So if I do that, you can see that I define the function, and so I call it f1 of x, so that now when I go into my CAS and select the f1 of x function, it'll be already drawn on the calculator. So now if I go to the graph on the calculator, we can see that we get a graph of the flight of the ball. So what is important though is in your window settings is you need to define the window that will show the key features of the graph. So I know that my ball starts from the origin, so I put -1 just so I can see that vertical axis, and I know we catch the ball 60 metres later, so I put the maximum x value of 65. For the y values, well, obviously the ball's not going underground, so again I just put -1 just so I can see the horizontal axis, and then you can see that I've just picked the maximum height of 30. Now I could have picked 15 perhaps, I could have picked, well, as it turns out I couldn't have picked 15, 60, just something to give me a look at the key features. So then to find the maximum height, we go to find that value there, analyse the graph. We analyse the graph, we find the maximum, and we can see there straight away that the maximum height is 15.4 metres. Okay? Now the last part of the graph says find the height of the ball when it is 5 metres horizontally before it hits the wicket keeper's gloves. So we're hitting the wicket keeper's gloves here at 60. So 5 metres before that is at x equal to 55. So really what we're trying to find out using the notation that I've got, I want to find out the rule for the equation at x equal to 55. So we haven't covered function notation much. So really what we're saying at x equal to 55, y equals. So if I substitute x equal to 55 in, y equals -13 on 875 times 55 squared, 156 on 175 times 55 plus 2, and that will give me of 213 on 55. So that's approximately equal to 6 metres. So it's about 6 metres in the air before it reaches the wicket keeper.